Hello everyone, and welcome to the fourth lecture of the Introduction to Media Engineering course. So after we covered in the last weeks or the last lectures the idea of how we can represent digital data and different types of media, including images, video, animation, audio, and text. So now we start moving to talking about each one of these types of media specifically in more details. So in this lecture we are going to start with digital still images and the details of how they are represented and different operations that we can do to digital still images. Okay. So as mentioned in the last lecture, digital still images can be modeled in two different ways, either vector graphics or bitmapped images. As we said, in bitmapped images, we represent an image as a two-dimensional array, where every location in that array would represent a point or a pixel in that image, and we store the color of that pixel in that location. Whereas the vector graphics, we represent shapes not using the info about every single pixel in the image, but we actually try to use some mathematical representation of the different components of the image. Okay, so we're going to talk in detail about this in this lecture, specifically starting with the vector graphics, and then we will talk afterwards about bitmapped images. So the vector graphics techniques, they are actually used by PDF files, SVG, the scalable vector graphics, and SWF, which is actually used to create flash movies. In vector graphics, images are built up using shapes that can be described mathematically, as we mentioned. Now let's see how images are represented. So each pixel in a rectangular array can be identified by its pixel coordinates. In vector graphics and even in images, the bitmapped ones, we always assume that the origin, which is the very first pixel in the image, is the top left pixel. So this is column number 0 and this is row number 0. Okay, so the numbering starts from here, and this is column 1, 2, 3, 4, and so on. This is row 0, 1, 2, 3, 4, and so on. Okay. Now, the big difference between the pixel coordinates and the real coordinates is that in pixel coordinates, the positions are only integer numbers. Like we have a row number and column numbers. It can be 0, 1, 2, 3, and so on. There is no fraction. While in the real coordinates and axes, we can have a real number to represent x and y. Like here, this point is at 2.35 and 2.95. Okay. So this is one difference, that when we talk about image representation in the form of pixels, rows, and columns, we're talking about discrete positions and also integer values for these positions, not continuous in the space. So first we have to talk about vectors. Given that this method is called vector graphics, then what is a vector? As we already know, the displacement between 2 points is a vector whose components are obtained by subtracting the x and y coordinates of the 2 points. So let's assume we have point 1 that has coordinates x1 and y1. We have point 2 that has coordinates x2 and y2. Then this vector connecting p1 and p2 will have in the x-axis coordinates, it will be x2 minus x1. This is the dimension on the x-axis direction. And the dimension on the vertical direction is y2 minus y1. So this is a vector connecting actually 2 points. So the term vector graphics was originally used to refer to the production of images on output devices using an electron beam that traces vectors on the screen. So this specific thing, actually, we will discuss it later on in the course, but let me explain this to you. So in old TV sets, I don't know if you have seen them before, but this is how they look like. If you look at a side view of a TV set, it will look like this, okay? Where this is actually the screen. So it's like a big box that has the screen in the front, and then we have something in the back, which is shown here, okay? These old TVs, they were called the CRT TVs, or the cathode ray tube TVs. So how do images get formed on CRT screens? We're not talking here about the LED screens that we are all using right now. We're talking about the old TVs, those box TVs In these ones, we would have some device in the back of the TV, and that device is actually emitting light to the screen that you actually later on you start seeing. Okay, now the idea of those devices, and let me look at as if we are looking at the screen from the front. So that device in the back, that which emits like an electron beam that goes directly and hits the screen so that you see the picture, the way it was actually working is that this beam sweeps the image from the top part of the image, like here, horizontally. Okay, so it goes like this. Once it reaches the end of the line, it goes down and then goes to the second line, down to the next line, down to the next line, and so on. Of course, the distances between these lines are too small, like because you don't see it. And that sweeping of the electron beam is done very fast, so that it's as if it's actually drawing the image on the screen without you noticing that this is happening. Okay? So the reason that they called this vector graphics is that, as we say here, so the term vector graphics was originally used to refer to the production of images on output devices using an electron beam that traces vectors on the screen. So that electron beam, it's as if initially it starts from this point and ends at this point. So it's like a vector connecting these 2 points. And then it goes down from this point here to this point here. So it goes through this vector, that vector, and then starts sweeping the image one more time, or the screen one more time, and so on. So as if the beam here is actually going through vectors on the screen to be able to plot. That's why they called it vector graphics. This was inspired by this idea in the beginning. Okay. Now the thing is about vector graphics is that we make use of the idea that lines and curves can be represented by equations relating the y and x coordinates of each point on the line or curve. So for example, the equation of a straight line is given by y equals mx plus c, as we know, where m is the slope of the line and c is the intercept. So you're relating the y coordinate to the x coordinate, and any curve can be actually represented with this type of equation. So the main idea of vector graphics is that instead of representing images with the value of every single pixel appearing in the image, we make use of the mathematical description of shapes, as we will see during this lecture, to represent the shapes. Okay? So let's start by the equation of a straight line. A straight line can be defined through using its 2 endpoints only. Let the 2 endpoints be x1, y1 and x2 and y2. The equation of the straight line, as we know, can be obtained by subtracting y2 minus y1 divided by x2 minus x1, and this we put it equal to y minus y1 over x minus x1. So using that representation, all what we need to find the equation of a straight line is actually 2 points. Okay. Now the line or curve is drawn. This is how we draw it on an image, by setting the color of the corresponding pixels. So those pixels that lie on that line are actually colored in the image as determined from the general equation and the stored values of some parameters. So for example, this is how a straight line would look like on an image. Now one thing about this line that you might notice is that this line doesn't look like a smooth line. It looks like it has a black part here, and then the next position we have this like 2 pixels that are black, and then 3 pixels that are black, and so on. So it looks like the line has this stairway effect. It's not really a straight line. And why is this happening? Because you're trying to draw a straight line on a grid of positions, in that case grid of pixels. That's why you get those jagged lines. Okay, let's explain this more in the next slide. So we say here that a problem arises when the computed coordinates of a straight line do not lie on the image grid. They are not integers. So if you look at this line, as we said, this line would have this stairway effect. Why is this happening? So let's take this as an example. Let's assume that we want to draw a straight line on an image going from this pixel here to this pixel down here. Okay? So first, let's see what the coordinates are for these 2 points. As we mentioned, the first column and first row are always given the number index 0. So this is the first column has an index 0, the first row has an index 0 or a number 0. Now let's see the first point. What is the coordinates of this point? This point, if this is column 0, this will be column 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is actually column number 12. So the first point, its coordinates are 12 and 0. So why did I write the 12 first? Because now we are dealing with normal coordinates. Now this is your x direction and this is your y direction. So the x value here is 12, the y value is 0. Now how about the other point, which is actually down here, this pixel. If you count the rows, it will find that this point is at x equals 0 and y equals 30. So these are the 2 points. Now we would like to get the equation of a straight line connecting these 2 points. We're going to use the equation y2 minus y1 over x2 minus x1 and so on. So y2 is 30 minus y1, which is 0, divided by x2, which is 0, minus 12 equals y minus 0 over x minus 12, right? Now if we do the cross product, you will have negative 12y equals 30 multiplied by x minus 12, which means that y is equal to negative 30 over 12 multiplied by x minus 12, right? So to get the final form, let me erase this here. So the final equation, if you get this means that y is equal to a negative 30 over 12 multiplied by negative 12, you get actually 30 minus negative 30 over 12 multiplied by x. If you divide both numerator and denominator by 6, you get 5 over 2x. So this is the equation of the line. Okay, now we have the equation of the line that has these 2 points as end points. The next thing is to draw that line on that grid. So let's see how this operation goes. What we normally should do is that we should substitute with different values of x. For example, if you put x equals 0, of course you get y equal 30, which is expected. This is one of the endpoints. Now what will happen if you put x equals 1? X equals 1 means this is the point that will lie on the column number 1 on the image. If you substitute with x equals 1, you get y equals 30 minus 5 over 2. So it's 30 minus 2.5, you get 27.5. Now what's the problem here? The problem is, given that we're talking about an image, a grid of pixels, then these coordinates, they have to be integer values. We don't have a value for y, which is a raw number, that's equal to 27.5. So how can we deal with this issue? We need to get rid of the fraction. Of course, there are multiple ways. You can approximate to the nearest integer. You can do floor, you can do ceil, and so on. So let's assume here that we're going to floor the number. Floor the number means that we go always down to the nearest, the least integer here. So in that case, y would be equal to 27 if we do floor. Okay, so we're rounding down in that case. Now this means that at column number 1, we should have a pixel at row number 27. Okay, so where is that on the image? So this row, the last one, this is supposed to be row number 30. This one is row number 29. The one above, this is row number 28. So where is row number 27? It's the next one, which is actually this one here. This is row number 27. So at row 27 and column 1, we are going to have a pixel in that case. So where is that pixel? It's actually this one. This is at column number 1, row number 27. So which means that now the first pixel that will be on the line is this pixel. The second pixel that we are drawing using that equation is actually this pixel. So what about the rest, the other pixels? I'm going to explain what this is, but now, for now, the first pixel on the image is this one. Second one is this one. Now let's go the other way around. Let's go for the other extreme. So here, this point is at x equals 12. When x is equal to 12, if you substitute, of course, in the equation, y would be equal to 0. Now, what if x is equal to 11? Now we're talking about the column before the one of the last pixel. If you put x equals 11, multiply by 55, you get 55 divided by 2, which is 27.5. You get y equals 2.5. Now it's the same problem. We don't have a row on the image that has an index or a number equal to 2.5. This is not actually possible. So therefore, we have to approximate this, and in that case, we do also rounding down, you go to 2. So this means that the pixel that will be on the column number 11, this column here, it will be at row number 2. So if this is row 0, this is row 1, this is row 2, this would be that pixel. So we have this pixel here, and we have this pixel here. Okay, so this is the pixel on column number 12. This is the pixel on column number 11, and this is the pixel here on row number 1, and this is the pixel on row number 0. So you can see the problem here is that those pixels that are appearing, they have some sort of discontinuity. Like we're talking about, this is the first pixel around this point, second one is this one, and here this is the last one, and this is the one before. So there is discontinuity actually between the pixels that appear on the image. And the way we solve this is by trying to fill the gaps in between those pixels. We try to fill them with black pixels, as you can see. Let me erase this and go with the text on the slide. It actually explains what I just mentioned. Let's erase all of that. So we say here that in this example, the endpoints are at 0 and 30 and 12 and 0, and therefore the equation of the line, as we explained, is 30 minus 5x over 2. By substituting with the values for x from 0 to 12, we will get real numbers which must be rounded down to lie on the discrete image grid. So what we normally do to draw the line, we substitute x equals 0, 1, 2, 3, 4, up to 12. Okay. Now to get a continuous line, and this is the whole idea, because if the line would appear as this pixel, and then this one, and then for example this one, then there will be gaps in between. So when you view that line, you wouldn't feel that this is actually a straight line. So to get a continuous line, we set blocks between 2 and 3 pixels to the desired color so that the straight line is approximated. So if this is your first pixel and this is your second one, then one thing you can do is that to fill these two, okay, so put this as a black pixel, put this one as a black pixel, and then when it comes to this one, you put this one as a black pixel. So now this appears as if it's a continuous straight line. Although what you will get from the equation is this point, and probably this point, and this point, and this point. All of the other black pixels, they are actually filled by, of course, the tool that does the vector graphics in order for the line to appear as a continuous straight line. Okay, so this is the problem that happens in general when you try to draw lines on a grid that has integer rows and columns, and this is how it is actually solved. Okay, so now given that those straight lines now do not appear really smooth and they have what we call the jaggeds or this stairway thing, then how can we solve this? How can we make this line look like as if it's really something continuous and smooth? So rendered lines, those lines that get drawn on a computer screen, will exhibit the jaggeds, as we said, a form of aliasing, a noise type, caused by the inevitable undersampling when rendering on a device with finite resolution. So once you try to draw something on a finite resolution device like this, these computer devices or whatever that have a certain number of pixels possible, then you might get this issue of the jagging. So the jagged lines. So how can we solve this? The effect can be resolved by what we call anti-aliasing. Coloring pixels in shades of gray for a black line whose brightness varies according to the extent of their intersection with an idealized 1 pixel wide line. So let's read this one more time. We're trying to color pixels around that straight line that we're drawing in shades of gray, and the brightness of those pixels will vary according to the extent of their intersection with an idealized 1 pixel wide line. Let's see an example. Let's look at this line. This is one straight line that's drawn on a finite grid, and you can see because of that you're drawing every single pixel, and although this is actually continuous, but now when you look at it this way, it looks like this is what we call the stairway effect. It's not really a smooth straight line. So how can we reduce that effect? If someone views that image, might not actually get the feeling that this is a straight line, might actually feel that this is in fact a stairway thing. So here's what we do. We first, in order, and this is also done by the vector graphics software, the rendering part, which is, it does it as follows. Let's first draw the straight line, the ideal straight line that we should have drawn if we were drawing this on, for example, a piece of paper. So this line is the line that connects all of these pixels together, right? And then after we draw that straight line, we make a rectangle around that line where the, as we say here, that rectangle will be intersecting with the pixels that are actually forming the line, which are these pixels, and the surrounding pixels as well. And what's next? So we do this line bounding box. What we do next is, if we have one pixel that is completely inside the rectangle, like this pixel, this one, this one, this one, these ones are colored in black. Now, how about if a pixel is not completely inside this bounding box or this rectangle? We will color it in the anti-aliased image based on how much intersection that pixel has with that rectangle. So for example, if you think about this pixel or this one, any of these pixels, half of them, okay, this triangle, half of them is inside the rectangle, the bounding box, the other half is outside. So we will color this pixel with a gray level of half. Like for example, if we assume that the gray is from 0 to 255, then 128 is just in the middle. So we will color these pixels in 128. How about, for example, this pixel? You see this pixel, actually 1/4 of the pixel only is inside the rectangle. The rest is not. So we color that with 1/4 of 255, which would be a light, or we can do it actually the other way around. So to make this light gray, then we can, okay, do it like at 1/4 of the range from 0 to 255. So if you divide 255 by 4, you get something around 64. So we will color this pixel with 64. Okay? Now, so again, this is what we are doing. In order to reduce the effect of the jagged straight lines, those stairway thing, we are going to draw that straight line and then find the intersection between the pixels and that bounding box where the line is running just in the middle through that bounding box. Depending on the degree of intersection, we're going to color the pixels in the anti-aliased output. Okay? So again, this pixel, 50% of it is inside the rectangle. We will color it with 128, which is midway gray. While this pixel, only 1/4 is inside the rectangle, so we'll color it with 64, which is 1/4 of the range to 255. Okay? So you might be wondering, okay, how would that solve the problem? I still see here the stairway effect. However, the stairway effect here is much less, as we will see in the next slide. So here we applied this anti-aliasing to the line that we had like 2 slides back, and then we zoomed out like as if we are looking at them from a distance. Now, when you look at this image, it's clear and obvious the stairway effect. Clear that this line is not a straight line. It's not really a smooth straight line. However, when you look at this one, this is after the anti-aliasing. Now, when you view this from a distance, it appears to you that really, yes, this looks like it's a smooth straight line, not like this one. This one, the stairway thing is really clear. Here it's not. So why is it not clear here? Because we did this thing. We did this property of coloring the pixels with different colors to give actually the effect of the or reduce the effect of the aliasing. So you remember when I said 2 slides back that we, to make the straight line, we start coloring the first of all, the pixels that lie on the equation are really colored in black, and then we fill the gaps. Now, when you are filling the gaps, you can fill them, instead of filling them with black pixels, you can fill the gaps with grayscale pixels, and that would reduce actually the effect of the aliasing issue. Okay, so this is all about anti-aliasing and how we actually draw straight lines in vector graphics and how we solve the problem of having jagged straight lines. So to your eye, this might seem as if it's a really smooth straight line. Okay. So we next discuss how we actually draw other objects other than straight lines. So drawing programs and vector graphics language, they provide a basic repertoire of shapes that can easily be represented mathematically. The common shapes other than straight lines, of course, are rectangles, squares, ellipses, circles, straight lines, of course, and Bezier curves. So let's look at that. So for example, if you would like to draw a rectangle, even actually on PowerPoint, if you try to do that on PowerPoint, the way you do it is that you would press on or click on one position. This would mark the start of the square, and then you start dragging the edge, right? And that by dragging this, you're actually defining the other point, the opposite vertex of that shape, whether it's a rectangle or a square. Okay, so by defining 2 points, we can easily draw a rectangle or a square. All what we need in order to define a rectangle or a square is 2 points on that rectangle, okay, which is x1, y1, this vertex, and x2, y2, this vertex. The width, of course, would be x2 minus x1, the height would be y2 minus y1. Now, the good thing about vector graphics, and this is the whole point of doing vector graphics, is that in a normal image, a bitmapped image, you will have to represent every single pixel that appeared in this square. So if we imagine that this square is divided into or represented in a 4x4 image, then you have 16 values that you need to store. However, if you would like to represent that rectangle or a square using vector graphics, all what you need to store is the value of x1 and y1 and the value of x2 and y2, and maybe the color of the square, and that's it. So you're storing here basically 4 values instead of, and then the color, instead of storing 16 values, the color of every single pixel on that square. This is the whole point of vector graphics, is that you can actually store things in a much, given that they are regular and geometrical shapes, you can store them with a minimum amount actually of information. Okay, and for example, one other example is drawing an ellipse. How do you draw an ellipse in an image? Again, it's the same thing. The way you draw an ellipse on, for example, Paint or PowerPoint, for example, you click on one position on the screen. This would mark x1 and y1, and then you drag a rectangle. So with the mouse, you're actually dragging or drawing a rectangle, defining the other point x2 and y2. Actually, using x1, y1, and x2, y2, we can easily draw an ellipse. Why? To draw an ellipse, you need actually 3 pieces of information: the center of the ellipse, and the radius in the x direction, and the radius in the y direction. So what is the center of that ellipse? It's easily would be x1, this point, plus rx, and y1 plus ry. So how about what is rx and ry? What is the radius in the x direction, radius in the y direction? It's easy. The radius in the x direction is the difference between x1 and x2 over 2. If this is x2 and this is x1, the in-between difference is x2 minus x1. If you divide it by 2, you get the radius. So this is the radius in the x direction. The same thing for the radius in the y direction. So the center of this ellipse would be at x1 plus rx and the y1 plus ry. So in general, in order to draw an ellipse, all what you need to do is these 2 points, the coordinates of the first point here and the second point here. And drawing, of course, the vector graphics platform will do the drawing thing. So if you, for example, in PowerPoint, if you choose that you are gonna draw an ellipse, you click on the ellipse shape, then the code that will run is a code that will be able to draw that ellipse given x1, y1, and x2, y2. Okay? So these are how we draw rectangles and how we draw ellipses as vector objects. Now, the previous examples we were talking about regular shapes like triangle, rectangle, ellipse. Now, what if I would like to draw curves in vector graphics? So is there a way to draw curves in vector graphics? In fact, yes. There is something called the Bezier curves, and Bezier is the name of the guy who put this method. Okay, so Bezier curves are smooth curves that can be specified by an ordered set of what we call control points, where the first and the last control points are the curve's endpoints. A cubic Bezier curve would have 4 control points, 2 endpoints, and 2 direction points. So let's see this as an example. Let's assume you want to draw this curve. So this is how it's done. You click in the first position, and then you draw a straight line that will end at this position. Okay, so that will actually draw a curve here. Okay, now the third point, when you do this, then the curve will start bending. Okay, because you clicked on this point, and then when you click on the last point, then the curve will be connected to that point. So you can try this actually even on PowerPoint or in Paint. There is a tool that will allow you to draw curves, and actually, in fact, what it's actually using is the Bezier curves. So P1 and P4, the first and last control points are the curves endpoints, while P2 and P3 are called the direction points. These are the points that define direction. So for example, if P2 was here, okay, let's assume that someone said, okay, I'm gonna do P1 at this point, and then I'm gonna do P2 this point. So the curve would be like this. The curve will always get closer to P2. Then when you do that, then the curve will start bending. So this is how the curve would look like compared to the bottom curve here. Okay, so this is it's called a cubic Bezier curve because the order of the curve is always equal to the number of control points minus 1. So if you have 4 control points, then it's called a cubic Bezier curve. So cubic means 3, so 4 minus 1 is 3. Okay. This is here how cubic Bezier curves are drawn by dragging direction lines with the pen tool. So this is what happens is that you click on this point and then you drag a straight line. You see, like as I explained, the curve will be like this, and then when you draw the other line, the curve would bend the other way around. And as I mentioned, the order of the 4 points of a cubic curve determines the shape. The degree of a Bezier curve is 1 less the number of control points. We have also what's called the quadratic Bezier curve, and in quadratic Bezier curves we only have a single direction point. So we have 2 end points and 1 direction point. So you click on this point, then you click on this point, and then click on this point, you get a curve that is like this. It's tangent to this line at P1 and tangent to this line at P3, and in between it has a perfect curve. Okay. The quadratic Bezier curves, they are actually the only Bezier curve supported by the SWF that gets used to make Flash movies. PDF and SVG, they provide both cubic and quadratic Bezier curves. Okay. Now, using Bezier curves, you can actually combine multiple of them to have a smooth path. So, for example, Bezier curve segments can be combined to make smooth paths. A closed path joins up on itself, and open path does not. So here, as you can see, we are connecting a cubic Bezier curve to another cubic Bezier curves, and these are how they connect together. And here also we are joining 2 other Bezier curves. So you can actually make very complex shapes by connecting together these Bezier curves when actually done on the vector graphics platform. Okay. One other thing that we can do also in vector graphics is that we can apply a stroke to a path to make it visible, specifying the width and color. We can also fill closed paths with colors, gradients, or patterns. Like here, we are filling with gradients of colors, and here we are filling complex shapes. All of that is easy to be done in vector graphics because once we define a shape based on an equation or based on some points, it's easy to identify all of the points that are within the boundaries of that shape and then fill them with any color or any shape that we want to have. Okay. Now, one other thing about also vector graphics that is easy to be done there is transformations. In fact, what we will discuss right now about transformations is also applicable to bitmapped images, as we will see later. So vector objects, they can be altered by changing the stored values used to represent them. We can use what's called the affine transformations, which preserve straight lines and keep parallel lines parallel. Examples of these affine transformations are translation, scaling, rotation, reflection, shearing, and let's see what these are. So for example, let's assume you have this shape defined in vector graphics. So what would be scaling? Scaling means that you are changing its size, either increasing its size or decreasing its size. So this is here a scaled up version of this image. Okay. Now when you look at the scaled up version, as we said, what affine transformation means that we are preserving straight lines. So a straight line would remain as a straight line, and we keep parallel lines parallel. So this edge and this edge were parallel. They are still parallel here in the scaled up version. Now rotation is to rotate that object. Here we are rotating it about its center maybe with a certain angle. Still parallel lines remain parallel and straight lines remain straight lines. Reflection is like you are reflecting, as if you have a mirror here and you're reflecting that object. Shearing is what is shown here. It's like you're stretching the image or the vector from one direction. In fact, you are stretching it in this direction and keeping the other direction the same. And finally, translation. Translation is just removing one object from one point to another. Okay, so if we have the objects defined using vector graphics, all of these operations are very easy to be done. So let's see some of them in the next slide. So actually, any of these transformations can be defined by simple equations. So let's start with translation. If you have an object, a vector graphics object, in a specific location in the image, and you would like to move that object from that location to another one. So to move an object by delta x to the right and delta y downwards, we change each stored point x, y to x plus delta x and y plus delta y. So as a very simple example, let's assume these are our dimensions. This is x and this is y. And let's say we have a point here, and that let me use a different symbol here. Okay, let's assume this is our point, and this point is defined by some x value and some y value. Let's assume the y value is 2 and the x value is 3. So what will happen if you add to the value 3, you add another 3, and the 2 you add 1. So this means that now you are at x equals 6 and at y equals 3. So this would be the new location of the point. So this is what translation is. So what you will do is that you will take the color of that pixel and move it to that new location in that case at 6 and at 3. Okay? Translation is very simple if you would like to do it. Now, what else? What is the other operation? We can also do scaling. So by scaling, we mean that we are actually changing the size of the object, as we saw in the previous slide. So let's have an example. Let's say again, this is our x-axis, this is our y-axis, and we have here a square. Okay, let's assume, okay, this is how it looks like. Okay, now we want to take that square and then double its size. And let's assume that the vertices of the square are at, let's assume this point is at 1 and 1, okay? And the other point, which is here, this is at 3 and 3, okay? So this is actually a 2 by 2 square, okay? Now, what if we want to make this square, we want to double its size. So to increase the length in the x direction by a factor of sx, and in the y direction by a factor of sy, we change each xy to be sx multiplied by x and sy multiplied by y. So what does this mean? Let's assume that we want to change the length in the x direction by a factor of 2 and the y direction by a factor of 2. So as if sx that we are applying here is equal to 2, sy is equal to 2. So the point that is at 1 and 1, if you apply this equation here, which says you multiply the x by sx, the y by sy, then sx and sy both are 2, then you get here 2 and 2. How about the point at 3 and 3? If you multiply both by 2, you get actually 6 and 6. So now, if you go and draw a square that starts at a point 2, 2 and ends at 6 and 6, how would that square look like? So let's assume this point is 2 and 2. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it's as if we have a square from here up to this point. This is how the square looks like. Now this new square that I draw is actually, in fact, yes, it is actually double the size of the original square, right? Why? Because it starts from 2 and ends at 6, meaning that the length of any side of the sides of the square is now 4 instead of 2. So this square has a length of 4, while the original one had a length of 2. Now that's how we actually scale up a square. Now there is one issue with this, that now the square is not in its original position. This square was actually starting here. Now in this image, that square is now in a different position. So you want that square to go back and be in its original location. So what we have to, as explained here, a translation must follow to move the object to its original position. So we have to take that square and translate it back to that position here. So which the translation that we explained here. So in fact, what you want to do is the point that's now at 2 and 2, you want to move it to 1 and 1. So what you will do is, after you do that, you put delta x, you do a translation with delta x equals -1 and delta y equals to -1. Once you do that, so every value like 2 and 2, if you subtract 1 and 1, you'll go back to the point 1 and 1, and the whole square, you'll do that actually for all of the pixels on the square. The whole square will be shifted, and now it will be at this point here. Okay, so this is what scaling is. So we talked about translation and we talked about scaling, how we can increase. Now, what if you would like to reduce the size of something? In that case, sx and sy, they have to have a value less than 1, like 0.5, 0.6, 0.4, and so on. Okay. Another thing, what if sx and xsy, they are fractions? So therefore, if you multiply the coordinates by that fraction, for example, let's assume sx was 1.5. You want to increase the size of the square by a factor of 1.5. If you apply this equation, then 1 and 1 will be multiplied each by 1.5. You go to 1.5 and 1.5, and we know that there is no point 1.5 and 1.5 on an image. So therefore, we have also to do an approximation similar to what I explained when we talked about the idea of drawing a straight line in vector graphics. Okay, so this is translation and scaling. We still have one more operation to talk about, which is rotation. So for rotation, we would like to see how we can rotate a point x and y, defined by the location x and y, around the origin by an angle theta in the anti-clockwise direction. So let's have an example. Let's assume we have this point x and y, and this point we are supposed to rotate it around the origin by an angle theta. So what we would like to do now is we would like to know where would be the new location of this point after rotation as a function of its original position and the angle of rotation. Like, for example, if we go back to this example, this is the new location of a point after translation. Here, this is a new point of a new location of the point after you do the scaling. Now, if I would like to write an expression or something like x and y of a point after rotation by an angle theta, what would be that x and that y? So we can actually prove this mathematically, given the figure that we have in front of us here, which is if we assume that x prime and y prime, these are the new locations of the point after rotation, then what we want to find is what would be the value of x prime and what would be the value of y prime. As a function of what? As a function of x and y, the original location of the point, and the angle of rotation, which is theta. So how can we relate x prime and y prime to x and y and theta? So if we look at this figure, and let's focus on x prime first. What is the value of x prime? X prime, we can, as we can see from this triangle here, see this triangle? X prime is that distance down here. So this distance is the value of x prime, right? So x prime can be written as L, right? Assuming that the distance between, and this is one thing that actually I also forgot to mention, which is if you are rotating a point that has a distance L to the origin, around the origin by an angle theta, then when you do that rotation, the distance between the new point that represents the new location of x and y and the origin, that distance will be the same because you're rotating around the origin. So it's like this is a radius of a circle, right? So therefore, if that distance is equal to L, here also that distance would be equal to L. So x prime in that case would be L multiplied by cosine of the angle, which in that case, this angle is theta plus alpha. This is the value of x prime, right? L cosine theta plus alpha. Now, as I said, the objective is that we want to get an expression for x prime as a function of x, y, and theta. We don't want this alpha thing, okay? So how can we get rid of the alpha? We can say here that x prime is equal, we can expand the cosine or use the rule of the cosine of two angles to say this is equal to L cosine theta cosine alpha minus L sine theta sine alpha. Okay? So we used here the rule of the summation of angles inside the cosine. So it's L cosine theta cosine alpha minus L sine theta sine alpha. Now, how would that help us in getting the expression for x prime and y prime? Let's look at here the full solution. So it says here that okay. So as I said, x prime is equal to L cosine theta plus alpha, which is equal to L cosine theta cosine alpha minus L sine theta sine alpha. Now, one thing about L multiplied by cosine alpha is that if you go to this triangle, you see this triangle here, this one, L cosine alpha is equal to x. Remember that this is the value of x, that distance is x. So L cosine alpha is in fact equal to x. Same thing, L sine alpha is equal to y. Why? Because you know cosine alpha is equal to x over L. So therefore Lx equals L cosine alpha. So we can remove L cosine alpha from here and put x, and remove L sine alpha from here and put y. And therefore x prime would be equal to x cosine theta minus y sine theta. And y prime would be x sine theta plus y cosine theta. So now we have an expression that relates the new location of the point xy after rotating by an angle theta as a function of what? X and y, the original position of the point, and the angle of rotation, which is theta in that example. Okay? So this is how we can do translation, how we can do scaling, and here this is how we can do actually rotation by an angle theta in the anti-clockwise direction, and that rotation is around the origin. Okay, once you do the rotation, then that point will be coupled, the brightness of that pixel will be coupled to that position, and this is how we get the rotated object. Okay, so this is all about the vector graphics part that we covered here. Next we'll move to the bitmapped image representation. So when we talk about bitmapped images, and as we said, bitmapped is or bitmapped representation is much better when you are trying to represent a picture, something that you are captured using a camera. Vector graphics is more suitable when you're drawing on a computer screen or using some computer to create shapes and objects. Okay, but when it comes to capturing images using cameras, then bitmapped images are much more, or bitmap representation is much more suitable. Now, when we talk about this, then we have to mention something called the resolution, which the resolution is a measure of how finely a device approximates continuous images using finite pixels. You know, like when you go and buy a new mobile phone, you will find that says, okay, this phone has a 25 megapixel camera, or 15 or 12 or whatever. So what does it mean to have 25 megapixels in the camera? This is, in fact, we are the megapixel thing is that you are actually defining the resolution of the device. In fact, there are two types of resolutions that we want to talk about. There is the device resolution and the image resolution. So what's the difference between the two? The device resolution is for a camera or even for a scanner. It's how far apart two lines on a target grid have to be for the device to see them as two lines. So imagine you're taking a picture with a camera. So how far apart two lines have to be from each other in order for the camera to be able to detect that these are two separate lines. Same thing for the scanners. Okay, so let's see, for example, the resolution of scanners and printers is usually measured in terms of what's called their pixel density, which measures how many dots we will have per inch. They call it sometimes DPI. So when you go and buy a printer or you buy a scanner, you will find that there is a number that tells you the resolution of that printer or scanner, which is how many dots, in the case of printer, how many dots this printer can print per inch. And for the scanner, how many dots for the scanner can actually scan per inch and store. So this is called the pixel density. Like here, this is a 72 dots per inch, for example, output from a printer. Okay, and this is 300 dots per inch. Maybe here you don't see the dots, but actually if you look at the PDF file and zoom on it, you will see that there are actually dots. So a 72 dots per inch means that this printer can print in 1 inch 72 dots, while 300, it can print 300 dots per inch. So obviously, as the pixel density increases, you get actually a higher resolution. So for scanners and printers, the device resolution is defined using the number of dots per inch. Okay. Now, the measure of resolution for when it comes to computer monitors, for example, is different. So as I said, printers and scanners, we use dots per inch. How about computer monitors? In computer monitors, we actually measure the resolution in terms of what's called the pixel dimensions, which is how many pixels do we have on the width and the height of the frame. So for an NTSC video frame, which is one of the famous video frames, they use a resolution of 640 by 420, meaning that we have 640 columns in that image or on that screen and 480 rows on that screen. A typical computer monitor can have 1024 by 768, again 1024 columns on the screen and 768 rows. Okay, so the pixel density is used for printers and scanners. The pixel dimensions are actually used for the monitors. Okay, the resolution of a digital still camera that you would have in your mobile phone is defined with something else other than these two, which is the number of megapixels. It's often quoted as the total number of pixels in the largest image it can record, and usually we measure it in megapixels. So as you can see, we have different definitions of resolution. All of them are device resolutions, but it depends on what device you are trying to describe. The resolution of the definition changes. Okay, so as an example, if we have a 5 megapixel camera, this 5 megapixel camera can produce images with dimensions 2584 by 1936. Actually, if you multiply these two numbers by each other, you get something close to the 5 mega if the aspect ratio is set to 4:3. And I'm going to explain what the aspect ratio is. Or it can display an image with 2736 by 1824 if the aspect ratio is set to 3:2. So what is the aspect ratio? The aspect ratio is the ratio between the width and the height of the image, where both width and height are represented in number of pixels. So this is a 3:2 aspect ratio. If you divide this length by this length, you get 1.5, 3:2. While this one to this one is 4:3. Now, a 5 megapixel camera, when we say 5 megapixel, this means that we are not really defining the aspect ratio or the exact size. We are saying that this camera is capable of capturing 5 megapixels. If you display the 5 megapixels in this size, which is 4:3, then the number of columns has to be 2736, number of rows has to be 1824. Multiply these by each other, get the 5 mega. And if you make it 3:2, then you get 2584 by 1936. Okay? So again, there is a difference between the aspect ratio of something and the resolution of the camera that captures the image. Okay? Now, the other type of resolution, other than the device resolution, and we saw it's different formats depending on the device, we have what's called the image resolution. The image resolution is simply the number of pixels that represent the image. So the pixel density of monitors and still cameras is assumed to be, let's assume 72 dots per inch. This is called the screen resolution. Okay. A bitmapped image has pixel dimensions but no intrinsic pixel density. If you have a bitmapped image that is stored on your computer, this image will have a certain number of pixels. Now you can take that image and display it on a screen that has a very high resolution, or you can take it and display it on a screen that has a very low resolution, right? So there is the physical size of an image, which means if you go on the screen and measure what is the width with a ruler, for example, how many centimeters this image would be, that would be the physical size of an image. The physical size of an image when it's displayed will depend on the pixel density of the device it is actually displayed on. So let's have an example. Let's assume we have an image and that image has 198 columns by 149 rows. If you take that image and display it on a device that is 72 dots per inch, this is how the image would look like. If you take the same image, same number of pixels, and display it on a monitor that has 115, or given that we're talking about dots per inch, let's assume we are printing. Okay? So if you're printing on a printer that has 72 dots per inch, this is how the image would look like. If you print it on 115 dots per inch, this is actually how it would look like. If, again, going back to the screen example, if we assume that the screen has a resolution of 72 dots per inch, then this is how the image would look like on that screen, and this is how the image would look like on the other screen. Now, how do we know that the width of that image is 70 millimeters and the height is 52.5? Where did this come from? So let's do the math. We have 198 columns, okay, and we have in every inch we have 72 dots. Okay, which means that we have 72 pixels. So the width is 198 pixels, right? So, and you have 72 dots, meaning that you have 72 pixels per inch. If you divide this by 72, you get the size of, or the width of that image in inches. So let me calculate this. Okay, so we're going to divide 198 divided 72. This is actually 2.75 inch. Okay. Now, to convert that into centimeters, then we will take the 2.75 and multiply it by 2.54, which is actually the inch. So multiply this by 2.54. We get 6.985 centimeters, which is approximately 70 millimeters. So this is where the 70 millimeters came from. Okay. Now you can do the same thing actually on this dimension. If you take the 149 and divide it also by 72, because when you say 72 dots per inch, it's this way or this way. If you divide the 149 by 72, multiply and so on, you get 52.5 millimeters. Now, what if you go to a higher resolution screen, a screen that has 115 dots per inch. So you will divide the 198, instead of dividing by 72, you're dividing by a bigger number, which is 115, and that's why you get here 43.5 millimeter. If you go to a 600 dots per inch display, then this is how the size would look like. So therefore, what we're trying to say here, the image resolution is the number of pixels that you have in the image. What defines the size of the image when it's displayed is the device resolution. So these two things, the device resolution and the image resolution, will tell us how the image would look like when it's displayed on a computer screen. Okay? So in general, the physical dimension, whether the width or the height, is equal to the pixel dimension divided by the pixel density, as we did. So we took the 198 and we divide by 72. This would give you the physical dimension. Most image formats, they actually record the resolution, which is the pixel density, together with the image data, and this is usually the resolution of the device in which it originated. If you right click on any image that you have on your hard drive and look at the properties, you will find somewhere it's written that you have 300 dots per inch. So what is that number? This number is telling you what was the device resolution that captured this image. Okay. Now, once we do this, then actually let's look at this example. Here we have two images. They look like they are images of the same scene. However, this one was taken with a device that has 72 dots per inch resolution, while this one was taken with a device that has 600 dots per inch resolution. Okay. Now, assuming that we're taking a picture of the same thing, so for if we take that image and display it on a 72 dots per inch screen, then it will be 198 by 149. This is the example that we had in the previous slide. Okay, 198 by 149 pixels and displayed on a 72 dots per inch screen. Now, that physical size of the image you can get with an image that has 1,654 columns by 1,240 rows. Okay, but it's actually displayed on a 600 dpi device. So if you divide 1654 by 600 and convert that into centimeters or millimeters, as we did in the previous example, you will find that once you divide 1654 by 600, you get the same value as 198 divided by 72, which means that the physical dimension of these two images is the same. However, this image has much more number of pixels compared to this one. How would you know that? If you go and zoom in on this image, for example, zoom in on let's say some region here, okay? Here, this is what you will get. You'll see pixelation. Why? Because you're zooming in and the number of pixels that we have here is not as many as here. Here, if you zoom in onto this image, you get this very high resolution. So although the two images, what we're trying to say here, although the two images might look to have the same physical dimension, however, still this one, okay, has lower resolution, because if we zoom in into this image, we'll see that we have actually much less number of pixels compared actually to this image. We get what's called pixelation. Okay. All right. So that's it for this lecture. We talked about vector graphics and we talked about the bitmap resolution. In the next lecture, we're going to continue that topic, talking about bitmapped images and how we can actually enhance how images look like and do some operations to them. Okay. All right. That's it. Thank you, and I'll talk to you soon.